Alrighty, we can go ahead and get started. So, before we get into the material for the day, just to let you know what's been happening, uh, this, I guess, over the weekend, I wound up getting sick, and apparently it wound up being COVID, which I'm still dealing with right now. Unfortunately, I think I had mentioned it in a previous class. I have an immune disorder, which makes me take immunosuppressants to lower my immune system to make sure that my immune system doesn't continue to attack my body. And when one of the problems, of course, with this is um, if I have a low immune system, it makes any kind of illness I get more dangerous than it normally would be. Now, with COVID, seemingly, I think I've gotten, I don't know which strain, but it must be the Omicron because it's not as bad as it could be, especially with what I have. Because if it was one of the original strains, then I'd probably wouldn't be around anymore to do any lectures. However, it's lasting longer than it normally would, as it would be expected for a person in my condition. And I'm not sure how much longer, but fairly sure I'm on the better side of everything. But I only say this. So first of all, that's why we didn't have class on Tuesday. I was not able to give an appropriate lecture. And in case something happens where we have to miss another lecture for some reason, just want to let you know that's why I'm dealing with this stuff. However, hopefully within the coming days, it should be fine. But certainly, I have to, stay quarantined and all of that stuff, especially longer than the normal 5 days they say. It's already been 5 days and I actually still have it, much less I'm over it. So we'll be continuing this online stuff certainly for the near future. And then I'm still going through the responses of the poll I had posted, and when I have that looked over and everything's fine with it, I'll let you know about if all the lectures will stay online. So far it's looking like it. So far all of the responses I've been getting have been either for online lectures or no real opinion on the matter. I haven't yet read someone who said they definitely do not want. So, but let me go through it before we make any final decision. But thankfully, at least we're just doing math review right now. So it's not like we're getting into some big new material that's we got to concentrate very much on. That would make the lectures a little bit more difficult. So today we're going to finish up the math review. Hopefully we're going to do trig and then vectors. And that should allow you, which is the other big thing to note, to complete the homework, which is due Sunday. So the homework was posted this past either Sunday evening or Monday, I forget when. And the deadline is Sunday, 11:59 p.m. So that's on Canvas. It's on the math review material. It's like 3 or 4 questions. And it's basically, a question on algebra, trig, and vectors. And it's to make sure that you're keeping up. You try some of the problems and you're reviewed enough in the math to get started with the actual physics stuff. So be sure that if you haven't already looked at it, to start looking at it and work on it, because even though it's due Sunday evening, you're more than welcome to turn it in whenever you want, just to get it out of your hair. So today, as I said, we're going to do the trig stuff, review it, make sure we know what part of trig is important, And the rest, of course, while some would consider important, it will not be useful to our purposes for the course. So the trigonometry we're going to talk about is basically the relationships for right triangles, or triangles that have a 90-degree angle in them, because that's the special case of the general normal triangle, which can have any angle it wants. The right triangles are a special case, and it makes the math a little easier. It takes what would be something like the law of cosines, a complicated looking equation, and reduces it down to something more easy like the Pythagorean theorem. And so these are the relationships we're going to be talking about. So for instance, let's say we have a triangle like this. Oh, by the way, can everybody see the screen? I want to make sure the whiteboard thing is showing up.
Yes.
All right.
Yes.
So let's say we have this triangle, and what I know about it is this side has a length of 4, this side has a length of 3, and this angle right here is a 90-degree angle. Now, what we may want to do is figure out what then must be the value of this side, the length of that side, what's the size of this angle theta, and this angle up here phi. Okay, so it's like a puzzle. When I see these types of things, I kind of like them because it reminds me of people that like Sudoku or crossword puzzles or whatever. You're given some pieces of information, and you want to use that information to find other things you don't know. As long as you know what rules or what relationships exist, this is not a big deal. So the first big relationship that I'm sure everybody's heard of, and it's called the Pythagorean Theorem. And what it is a relationship between the lengths, the 3 lengths of the side of a triangle. Turns out that by geometry, the 3 lengths are always related to each other in a very particular way, and that way goes like a squared plus b squared equals c squared. Nice, easy formula, but what does it mean? What is A, B, and C? Well, A, B, and C stand for names. We label the 3 sides with names. And so one of the sides is A, one of them is B, and one of them is C. Now, what you have to know is which one is the C. Because A and B, if you call one A and the other B, or you switch them, it doesn't matter. A squared plus B squared is the same as B squared plus A squared. Doesn't matter. The C is the weird guy. He's the one that's different. So we need to figure out which side is the one called C. And it turns out it's very easy to know that side is also called the hypotenuse. Now, I'm not going to be able to spell this correctly, I'm sure. Hypotenuse. So it's a very special side. It happens to be the longest side of the triangle, always. And the way you can tell which one is the hypotenuse is it's always the side which is opposite to the 90-degree angle. So for us, the 90-degree angle is right here. The side opposite it is that one right there, the one I'm calling R here. Now, why is that? Why is that always the biggest side? It turns out that there's a second relationship, and that relationship is between how big an angle is in a triangle and how long the side across from it is. And we can see it quite clearly here. If you look at theta, theta is a certain size, and it makes the side length 3, whatever it is. However, if I made theta bigger, so now it looks like this, obviously now this other side is going to be a lot longer than it was. So how big of an angle you have will determine how big of a side you have across from it. Now that piece of information, along with the fact that the biggest angle in a right triangle is always 90 degrees. The other two angles will always be smaller than 90. So 90 has to be the biggest angle. So if 90 is the biggest angle, then the side across from that will always be the biggest side. So it's really easy to see which one's the hypotenuse. Look for the 90-degree angle and the side across from it. That's your hypotenuse. Once you have that, this is very easy to do. We say, okay, I know R for us is the hypotenuse. So A squared, I'll say that's 3, plus B squared, let's say that's the 4, must equal C squared, which is the R. And now we have a nice little equation to determine the value of R. So 3 squared, that's 9, plus 4 squared is 16, is equal to R squared. And 9 plus 16, of course, is 25. But I don't want R squared. What I want is R. So I take the square root, and I get R must be 5. And so I now know how long the hypotenuse is. That length must be 5. And that's how you use the Pythagorean theorem. Of course, you're not always looking for the hypotenuse. Sometimes you know what the hypotenuse is. Maybe I knew R was 5 and the side at the bottom is 4, and I don't know the side on the right. You still use a Pythagorean theorem. It's just now I'm looking for A instead of C. Same thing. So that's our first big relationship, the Pythagorean theorem. It allows us to relate the 3 sides of a triangle. The other relationship we have is usually referred to, at least in the United States. I don't know about other countries. In fact, I know there are other countries that don't do it, but I don't know if other countries do. And that relationship is called Sohcahtoa. Sohcahtoa is just a way of standing for a series of relationships, 3 relationships, in fact. And it's broken up into 3 pieces, SOH, CAH, and TOA. Okay. It's very easy. SOH, that means the sine of the angle theta must be equal to, or is the same value, the number itself is the same as the side opposite, that's what the O means, opposite to that angle, divided by the hypotenuse of the triangle. So that's where the SOH comes from. Sine is opposite over hypotenuse. And so that relates one of the angles with some of the sides of the triangle. The CAH, of course, same thing. This one says the cosine of the angle theta is the adjacent side. Now, adjacent means the side next to instead of across from, divided by the hypotenuse. And then the last one, of course, is tangent of theta is the opposite side, or the side across from the angle, divided by the adjacent side, the side next to it. So that's the big set of relationships that allows you to relate sides with angles. Okay, so we have one relationship that relates all 3 sides. Here we have a relationship that relates some of the sides with the angles. Last little relationship you may or may not know is it's just a fact for any triangle. The sum of the 3 angles of a triangle is always equal to 180 degrees. So if we have theta plus phi plus the other one is always 90 because it's a right triangle we're dealing with, is always 180. Okay, so these 3 relationships will always be used, or some of them, but they're all able to be used to figure out stuff about the triangle. Okay, so let's do an example of the Sohcahtoa to try to calculate something about theta. So there's theta sitting there in our example triangle up here. And I say, okay, what do I know? Well, I know the side 3, that's the opposite side. I know the 4, that's the adjacent side. And I happen to calculate the hypotenuse, and that's equal to 5. So I actually know all 3. So that means I could use any one of these 3 relationships, sine, cosine, or tangent. Doesn't matter which I choose. But here's a little tip. And this tip is for future career advice. And that is, be careful about using an answer that you calculated yourself to solve for other things later on. And I say be careful instead of don't do it, because you can do it as long as you're confident that you got the right answer for the thing you calculated originally, then you're more than welcome to use it later on. And sometimes you have to, you have no choice. However, what you don't want, let's say you're an engineer, a friend of mine, she's an engineer, civil engineer, and what she gets a lot of time, she does a lot of the calculations for constructing bridges and things like this. And so she'll get a spreadsheet, and she has to, let's say she's working on a dock, and they want to make sure the dock is stable and it can withstand an impact from a boat running into it with a certain speed. And so she gets information about the materials, how the dock is made and stuff like that. And she goes in and does a bunch of equations and calculations about what if a ship is coming in, ship has a certain mass, runs into the dock with a certain speed at a certain angle. Will that break the dock, or will the dock withstand it? And it's a series of calculations down the line. But if she messes up towards the beginning with a calculation, maybe she inputs something wrong or the equation slightly wrong or whatever, then every other calculation below it is going to be wrong as well. And then if she goes and turns that in to her superiors, to the bosses, and it's wrong, then she gets in trouble and she can be fired for it, especially if a real life incident occurs. Whereas if instead her calculations are based on the data given to her, and she does not base those calculations on stuff she had to calculate herself, then either it's going to be right, or if it's wrong because the data she was supplied was wrong. And so that takes away her liability. So the same thing here. I could use, for instance, sine of theta. Sine is opposite over hypotenuse. So if this is our theta, the opposite side is the 3, and the hypotenuse I calculated to be the 5. I can do that. However, this relies on the fact that the 5 was correct when I calculated it. I happen to know it's correct. However, if I'm unsure, then what I'd rather do is say, no, I'm not going to do this just in case my 5 is wrong. Instead, I'm given the 3 and the 4. They have to be right. And that's the opposite side, and that's the adjacent side. So let me use tangent instead. Tangent of theta is the opposite side over the adjacent side. And now what I'm doing is using only those numbers given to me in the problem to solve for an answer. And as long as I do the work correctly, then I'll get the right answer. So that's just a tip. In general, especially in future career stuff, use data given to you when you can. If you have a problem where you have no choice but to use something you calculated, then just be sure you're doing it correctly. Now, I'm not done. I haven't actually calculated what theta is. What I've calculated here is what tangent of theta is, but I don't care about tangent of theta. I want to know theta. So how the heck do I get theta from this thing? And I like to do this, especially at the beginning of the semester, just to show what it is you do to get the theta out of this equation. And I relate it to this other thing. Say we have 5x equals 10. Okay, there's an algebra problem. We all know how to do this. Say, okay, divide by 5 and you get x is equal to 2. But why are we doing it that way? The reason you do it that way is because what we have here is an equation of 4x, but instead of having x, we have 5 times x. But I don't want 5 times x, I want x. So how do I get rid of the operation of multiplying x by 5. You do the opposite operation, or the inverse operation. And the inverse of multiplying is dividing. So I would divide by 5. And what that does is it cancels the operation of multiplying by 5. But then if I do it on the left, I got to do it on the right. So I have to do that dividing by 5 thing over here as well. And that's how we can get x by itself without that extra operation and get the answer. Now that process, that premise is what I want to do here. Here what I have is tangent of theta. So I'm operating on theta with whatever this tangent thing is. It's some weird function. But I don't want that. So how do I get rid of the operation of doing a tangent? Well, you do the inverse of a tangent. What's the inverse of a tangent? Thankfully, it's really easy. It's called inverse tangent. So you take the inverse tangent, and that cancels the operation of doing a tangent. By the way, sometimes you'll also see it called arctan. Okay, especially older textbook. When I was a student, I learned arctan before I learned inverse tangent. So some people, you may see arctangent or arcsine or arccosine. It means inverse sine, inverse tangent. But because I did it on the left, I also have to do it on the right. So this becomes theta now is by itself. I canceled out the tangent. But now on the right, I have this inverse tangent thing sitting here, acting on whatever was there. But that's why we have our calculator. Take out your calculator. I unfortunately don't have my calculator with me. But you take out your calculator, and where you have the trig functions, the second function is usually the inverse. So the thing above the sign is inverse sine, sine to the negative first power. That's how you do the. Now I think this is probably something around 36 or so, I don't know. But whatever it is in your calculator, that's the answer. First of all, make sure you're in degree mode. This is going to be true for the whole semester. We are not going to use radians ever. So if you're in a math class, which I'm sure you are, they almost always want you in radian mode, which is fine. When you're in physics, get out of radian mode because we're not going to use radians mode. We're going to use degree mode. But there you go. That's how you do this. So given a triangle, certain piece of information we know, certain piece of information we don't, and we want to figure out the unknown stuff. How do we do it? We make use of these three relationships. The Pythagorean Theorem for learning about the sides, Sohcahtoa for relating sides and angles, and then of course the angle requirement of 180 degrees is to get all three angles. If you know two, then you can always get the third. You just subtract 180 from the other two. And that's all the trigonometry we need. Okay, all the other stuff you learn when you take pre-calculus trig or high school trigonometry or advanced math or whatever it's called, double angle formula or the law of sines, law of cosines, we're not going to use any of that stuff. This is everything we're going to need from trigonometry. So are there any questions about the trig? All right, now why is this important? It's important not because we're going to be doing a bunch of trigonometry problems, but rather because we're doing vectors. Physics has a lot of vector problems in it. This semester, not as much as last semester, but there will be some vector stuff. And so that's a big, important part that we need to understand to make sure we can actually do this stuff when it comes up. And it turns out that in order to do vectors, all you need to know is how to do trigonometry because they're related very, very strongly. So if you remember from last semester, vectors goes like this. Vector is an object which contains two pieces of information, a magnitude and a direction. So for instance, the distance you travel, that's a vector. How far did you go? I went 300 miles. Which direction did you travel? 30 degrees north of west, something like that. So magnitude, how far or how fast, and a direction, in which direction did that thing point. And in general, vectors are shown as like an arrow pointing out into space from the origin. The length of the arrow tells you the magnitude, the direction, the angle that the arrow makes with respect to the x-axis generally is the direction. And so what kinds of things do we need to know about vectors? Well, let's say we have this vector here. This is 10. So maybe this is, you're at a campsite, you're sitting at your tent, and then you decide to walk 10 meters at an angle of 30 degrees north of east. Okay, so the angle here is 30, here's east, here's north, and you walk 10 meters out this way. Okay, and let's say you're with a friend, and the friend wants to meet up with you, but they don't know which way you went, so they're going to follow a trail to try to meet up with you. And the trails in this campsite happen to run either east to west or north to south. So what your friend wants to do is get to where you are by going straight to the east a certain amount, and then they want to go straight north a certain amount. And they want to get to where you are. And so the question is, how far should they go in this easterly direction? And how far should they go in a northerly direction? And I'll call that X and Y. This is a nice basic vector problem. Now, what we're going to do to solve this is actually something a lot more important, which is called finding the X and Y components of a vector. Okay, so I'm given a vector 10 meters at an angle of 30 degrees. And what I'm truly asking with this story is give me the X component of the vector and the Y component of the vector. Because that's what the components mean. The X component is how much of this vector points in the X direction. And the Y component is how much of my vector points in the Y direction. Now, how do we do it? Well, I gave you a big hint with this drawing. You start with the vector, and then you make a right triangle out of the vector where one of the sides is horizontal, the X side, another side is vertical, the Y side. That forces the magnitude, the hypotenuse, well, it forces the magnitude to be the hypotenuse. So the 10 now is the hypotenuse of this right triangle, and the angle, of course, is 30 degrees in this case. And so now all I have to do is use my knowledge of trig to solve the right triangle. And that will give me the components. So let's call this vector vector A. So vector A, X component. How do I do it? Well, I look at my triangle and I say, what do I know? I know the hypotenuse and I know an angle. Okay, so I know hypotenuse, I know the angle. And what is it I'm looking for? I'm looking for the X side, but is the X side the side opposite to the angle or is it the side adjacent? Well, obviously looking at the angle, X is next to it, so it's adjacent. That's the thing I'm looking for. I know these two things. So then I say, from Sohcahtoa, which relationship will I use? So I go up, I say, here's adjacent, here's hypotenuse, and I'm looking for theta, or I have theta, so I'm using cosine. So there we go. I would use cosine of theta is adjacent over hypotenuse. There's a relationship I want to use. However, let me plug the numbers in. Cosine of my angle, and my angle is 30 degrees, is equal to the adjacent side, which I'm calling X, over the hypotenuse, which is 10. And now you see I have my little equation. What do I want to do? I want to use this equation to solve for X. Well, it's really easy. Bring the 10 to the other side, and that leaves X by itself. So we have X must be 10 cosine 30. And there you go. Now, hopefully you did enough vectors in the first semester physics, but if not, hopefully over time, you'll get to where you're comfortable enough to skip this step and this step. That's the formality. That's how we get it. And just go straight to this. If I want the x piece of this vector, it's magnitude cosine of theta. Okay, because the x piece is the adjacent, and I know adjacent goes with cosine. So it's 10 cosine 30. I don't have to remember the original equation and do the algebra. Now, if I'm not comfortable yet, I do have to do it. So that's fine. Go ahead and do it. But just know that in general, what you'll find when I'm doing these problems, I just go straight to this piece right here. So if you're wondering, how did I know it's 10 cosine 30? Well, just go back to the original relationship from Sohcahtoa and then solve for the thing you're looking for, and you see that's where it comes from. So there's the x piece. What about the y piece? Same exact thing. I want the y side, so ay. What do I know about the y side? Well, the y side is the side opposite to the angle. Opposite from Sohcahtoa goes with sine. So it's going to be 10, the magnitude, times the sine of 30, which is, of course, 5. And that's how we do components. Very, very easy. It's nothing more than the original Sohcahtoa relationships from trigonometry, only now we're calling them more fancy terms, x and y components. You create a triangle out of your vector and then just solve for the unknown sides. Now, one thing you do have to worry about that we didn't have to worry about with this example is the fact that sometimes these things can be negative or positive. Okay, so let's look at an example where we have to worry about this. Let's say we have this vector right here, which is 20, and this angle, let's say, is 30 degrees right here. Okay, we'll call this vector B. And the question is find the x and y components of vector B. All right, so what is vector B? Its magnitude is 20, so it's 20 meters or 20 meters per second or whatever it is at an angle of 30 degrees west of north. And I want the x and y pieces. How do I do it? First step, either in your mind or draw it out. Make a right triangle. Okay, so one side is horizontal, one side is vertical. So there we go. I have my little triangle. Now note, I get this question a lot. So if you have this question, I'm going to try to answer it before you have to ask it. I get the question, how did you know to make your triangle like that rather than like this? That's a right triangle. And you can make that your triangle. There's nothing wrong with that. The problem is, however, in this case, we were given this is 30 degrees here. Well, if this is our triangle, that 30 degrees is not in my triangle anymore. So what I need to know now is that this angle here is 60. So it's an extra step. First step I have to do is figure out what one of the angles in my triangle is before I can go ahead and do the components. Well, why do the extra step? Just start, make your triangle with the given information in your triangle. And so that's why I use the original way I do it. Next, label the sides. The side that's horizontal is always the x side. So this one's the x, and the vertical side is always the y side. There's y. All right, so now we can get the answers. We want bx, the x component of b. So my angle of 30, the side x, is that opposite or is that adjacent? Obviously, it's across from the angle, so that's the opposite side. So Sohcahtoa says opposite goes with sine. So this is 20 sine 30, which is 10. However, here's where the rub is. Notice my vector B points up and to the left. So when we do X and Y components, up and down are separate from left and right. So when I'm looking at the X component, I only care about left and right. So forget about the up and down part. So my vector B is pointing to the left here. And left, as a standard rule in math, is negative. So I know my X component must be negative 10, not positive 10, because B points to the left. In this original example, A pointed up and to the right. So since it pointed to the right, it was positive. In this case, B points to the left, he's negative in the X direction. Now we do the same for the Y component. The Y side is the side next to the angle or adjacent, and adjacent from Sohcahtoa goes with cosine. So it's 20 cosine 30, 17.3. Now I look at the sign, is he positive or negative? Well, B points up, and up, of course, in math is positive. So he's just positive. So just because B points to the left, that doesn't make both components negative. It only makes the X piece negative. And in the Y piece, you look at its up and down. Is it pointing up or is it pointing downwards? So that's how to do components. Any vector you're given, draw it out on a coordinate system, make a right triangle out of it, label the sides X and Y, and then do Sohcahtoa to figure out the components. The other thing is the opposite. The opposite question goes like this. What if instead of knowing the vector, what I know is the components? Let's say I know that AX, the X component of A, is 5, and the Y component of A is 7. Okay. The question here is calculate the magnitude and direction of A. Okay, so I don't know what A is, but I know that A points in the X direction 5 and in the Y direction 7. And I want to know what's the actual vector. So if I were to draw this, it would look like this. In the X direction, he goes out 5. In the Y direction, he goes out 7. And so the vector must point something like that. Okay, here's vector A, and here's some angle theta. And I know that this side is 5, this side is 7. And now, again, I gave you a huge hint on how to solve a problem like this. It's still trigonometry. We want to know the magnitude, and we want to know the direction. Let's do magnitude first. Let's say this is a right triangle, and you want to know side A. First of all, side A is the hypotenuse of the triangle, obviously, because here's your 90-degree angle. So I'm going to use Pythagorean Theorem, and that says 5 squared plus 7 squared is my A squared. A squared plus B squared equals C squared, right? So 25 plus 49 is A squared. So A squared is 60, 74, square root of both sides, and you'll have your answer. Now, it's 8 point something. Now, what does this mean? If you were to see this as an equation, what you would usually see is magnitude of some vector A is the square root of the X component of A squared plus the Y component of A squared. All right, that's your big equation. for magnitude. But note, it's just Pythagorean theorem. That's all it is. X component of A, that was the 5. Y component of A, that's the 7. And the magnitude of A, that's the hypotenuse. Okay, it's just a Pythagorean theorem, but it looks like a fancy equation. So that's how you get your magnitude. What about the direction? Again, use trigonometry. If I want to know the value of theta, what do I know? I know the side opposite to the angle, and I know the side adjacent to the angle. So that tells me tangent of theta is equal to the opposite side over the adjacent side, which here is 7/5. So theta is the inverse tangent of 7/5. Okay. Just like before, there's no difference. Just because this is a vector problem doesn't mean it's not the same as what we did before. Pythagorean theorem, Sohcahtoa. In this case, we're having to use the tangent. Now, what does the equation look like for vectors? The direction of a vector is given as the inverse tangent of the y component of A over the x component of A. That's what the equation looks like. But you can see it's just the same trigonometry relationship from Sohcahtoa. Here we're using tangent because we happen to know the x and y components, which are the adjacent and opposite sides. So there you go. With these things, first of all, components, and then magnitude and direction, you have everything you need to do a vector problem. And generally speaking, a vector problem will go something like this. Here's 2 vectors, A and B. Add the 2 vectors together to give me vector C. Okay, now there's definitely a story. Maybe the story is you have 2 charges, 2 electric charges. One is positive 2 microcoulombs and the other is negative 5 microcoulombs. They're placed 3 meters apart. Calculate the total force between them. Okay, fancy story. Don't worry about how to do it. The equations involved, we're going to get to it. At the end of the day, what it's asking is, you have a force due to A, you have a force due to B, add those 2 forces together. Those forces happen to be vectors. How do we add vectors? Math tells us you can only add vectors if they point in the same direction. Since they're not going to point in the same direction, we do a trick. And the trick is take each vector in your problem, A, B, C, however many you have, and first break them into X and Y components. So that's this first part up here. Given a vector, give me the X and Y components of the vector. And then do the same for every vector. So now you have them all listed out. Then take all the X ones and add them all together. And that'll give you a total X component. Then get all the Y ones, add all the Y ones together. That'll give you a total Y component. So now you have some new final vector, his X and his Y components. Go here to magnitude and direction, say, I now know the X and Y components, give me the magnitude. I know the X and Y components, give me the direction. You have now successfully added the vectors together to get a new total equivalent vector or resultant vector. That's all there is to it. Yeah, what's up?
So the last one we just did, would that be 54.46?
Would it be 54? Let me think. 7 is bigger. Yeah, that sounds like it could be right. Unfortunately, I don't have my calculator with me. I have my phone, but I don't trust my phone to do these inverse tangents very well. But it seems okay. It should be something bigger than 45 because the 7 side is bigger, so it's going to be a bigger angle. So that sounds like it's correct. Yeah.
Okay, and the square root of 74, I got 8.6. Is that right?
Yeah, that's right. Because if you look, 9 times 9 is 81. So it has to be less than 9. And 8 times 8 is 64. So it has to be bigger than 8. So 8 point something sounds perfectly right. Very good.
Okay, thank you.
Mhm. So that's vectors, okay? Magnitude and direction have fancy little equations to them, but it's Pythagorean theorem and Sohcahtoa. Finding components, draw your vector, make a right triangle, find the unknown sides. Again, Sohcahtoa or Pythagorean theorem. And then what physics is going to do is take these tools, take these equations, and put a story to it. Instead of just saying what you would get in a math class is vector A is this, vector B is this, add them together to get vector C. That's boring. In physics, what you'll get is a person walks out of their front door at an angle of 30 degrees north of east for 15 meters, then turns and walks 4 meters due east. If he wants to get back to his front door in a straight path, in which direction and how far should he walk? Okay, it's the same problem. I have two vectors. The first vector is A, the second vector is B. I add those two vectors up. That tells me how far did he walk and in which direction. If he wants to come back, he just goes the opposite way. So you'll have a story to physics, some problem, but deep down within it, the mechanics of the story is, here's some vectors, do X and Y components on the vectors, add the X's, add the Y's, give me magnitude and direction. Forget about what the story means. The meaning of the story helps us think about how to do it. Why are we doing what we're doing? But the actual mechanics of it, the hidden details is we're just doing trigonometry here. Now, again, this is not going to be a big part of the class. This is really going to show up only when we talk about electricity and magnetism. But I wanted to show it now because it's a big part of that one topic. Very, very big part of that topic. The other topics, we won't have vectors. It'll be basic equations and stuff. So are there any questions about how to do this vectors? This is definitely something that you practice. It's really easy once you get to know it, once you're kind of used to the rules. Sometimes I see little issues where doing the components, a student will mix up the 30 and the 10, little things like that. Once you understand what it is you're doing, you'll see every single problem we do, you always do it the same way. So you get used to it, but you can't get used to it if you don't practice them. So practice them, become comfortable. It'll become boring once you're at the boring part, and boring because you know how to do it, not boring because you think the topic is boring, but just because you're kind of just doing it without thinking about it, then you're golden. You'll be an expert in vectors, and then you can just concentrate on the physical concepts that we're going to start learning. But that's all I have for the math review. So we did algebra, we did trigonometry, and then with trigonometry, we've now done the vectors. You now have all the math we're going to need for this class. Next week, we'll start into the new material. I think we're going to start with thermodynamics first. So just be prepared for that. If you want to look ahead, you're more than welcome to, but that's not necessary. Certainly, the homework is due Sunday evening by 11:59 p.m. So work on that, get that done whenever you can. And if you're having trouble, on Canvas are the previous recorded lectures on these math review things, as well as practice problems with solutions. So there's a lot of stuff there for you to look over if you're getting stuck. But separate from that, you're more than welcome to email me. If you're having trouble with something specific, take a picture of your work or whatever, send it to me and I can look over it and see where you're getting stuck or where you're getting wrong or something like that. But these first 2 weeks are pretty much just preparing us to start into the material. So I expect this homework is not a big deal. Next week, we start in the thermo, where we actually start getting some new material. And for anyone who's in chemistry, I think either you're ready for thermo because you do a lot of thermodynamics in chemistry, or it'll be very helpful because a lot of chemistry is thermodynamics. So we'll learn it. Some of it's pretty fun. Some of it's like, all right, whatever, but it is what it is. But it's not difficult, the types of stuff we're going to do in this class. When you get into high level thermodynamics and statistical mechanics and stuff, that's very high level math stuff. So if you're a physicist and you're going to take statistical mechanics, you get a lot of calculus, a lot of differential equations in there. For what we're going to be doing, we're doing things like the ideal gas law. We're doing things like calorimetry and heat transfer, radiation. These things don't require calculus. They don't require all that stuff. Algebraic equations are all we're going to need. So that's what you can expect from our first topic. Anyway, that's all I have for you today. If you have no questions, of course, you're free to go. If you do, feel free to ask before you go.
Thank you.
Sure.
All right, have a good one.
Thank you, you too.